All right, now we're going to talk about test two. So practice test two, just some kind of practice to get into it, to kind of get an understanding of what kind of questions I might be asking, what the format might look like. So it's always fair game for me to just be asking you arrow pushing questions. This is something that I can never really fully trust that people can do. It's trickier than it might seem from first glance. So, um, when I look at a question like this, I immediately see that this oxygen has gained a negative charge. And I see that this carbon, which had two hydrogens, now only has one hydrogen. So something has to take a hydrogen. Most likely it's this thing with a negative charge. And I'm going to ultimately give a charge to the oxygen. Um, this reaction is a little bit more complicated. This is actually the MCPBA reaction where we form an epoxide. So it's just the mechanism for it. I wouldn't ask you to know the mechanism. I do think this is missing a couple of arrows, to be honest with you. But the key idea here is that what this is showing is I have this carbon chain and this oxygen is bonding to that carbon, and the double bond here is forming another bond to that oxygen. So this shows a cyclic formation here of an epoxide. This is just the inverse of the reaction we just showed earlier. I'm not going to spend a ton of time on this because this is stuff that is a review, but really we need to come from an electron source, which is this double bond. I think the key problem people might have with a question like this is putting the arrows from here, but we don't want to do that because there's no lone pairs on this carbon, so the arrow has to start at an electron source. So it has to start at the double bond. So it's implied that we're adding a hydrogen here instead of here because that would break our octet. All right, this is a very similar question to the MCPBA reaction, where I'm going to draw the carbon scaffold here. I see that this bond is going to connect that carbon to this carbon, and this double bond is going to form a bond with that carbon as well. So you form the cyclopropane. This is another kind of ring forming reaction. And this zinc iodide is here. All right, so that's arrow pushing. These are things that were relevant to the particular unit that were kind of a little bit trickier than what I would want you to be able to provide on a, mechanism question. All right. This question is focused on this carboxylic acid and the kind of dual role that a carboxylic acid can play. So if we compare it to our chart, a carboxylic acid both has the carbonyl that indicates it could be electrophilic, and it has the oxygen, the OH that could be nucleophilic, right? So a carbonyl can play both roles depending on the conditions it's put in. This, even if you don't know what this is, if you see a metal, I would think base. So this is basic conditions where this is acidic conditions. Um, in basic conditions, what's going to happen is I'm going to remove that proton and I get a nice nucleophile, which means that I need an ethyl, right? So these two carbons, I need those two carbons no matter what. I'm going to balance the equation. And then since this is a nucleophile, I need that carbon to be electrophilic. So I'm going to put a leaving group on it to make sure that it's an electrophile, right? Likewise, over here in acidic conditions, this carboxylic acid is going to be an electrophile. So I'm reacting with this carbon, which means that I need this whole group to add in because that is what's binding to that carbon, right? In acidic conditions, this carboxylic acid is going to look like this. So I need that whole group to add in, and I'm going to just make it neutral with a hydrogen. I wouldn't make it basic because this is acidic conditions. So I wouldn't make it negatively charged because we don't need to. We want to keep it, it's acidic conditions, we want to keep it that way. So something interesting to note is that um, even though I get the same product going left and right, uh, this oxygen comes from what we add, where this oxygen comes from the starting material, from the carboxylic acid. And that just depends on what I'm reacting with, right? With one, I'm reacting with the carbon. With the other, I'm reacting with that oxygen, just depending on the kind of situation I'm in. Uh, this question is just trying to get you to see that with Grignards, if there's an OH present, it's going to um, deprotonate the carboxylic acid instead, and that's going to quench my Grignard. And no reaction can happen after that point.
I have a quick question. Is it not like Grignard specific? Can it be like any nucleophile?
Um, it's Grignard and LAH specific. So the problem is, okay, so let's go here, right? In this case, this nucleophile attacks that carboxylic acid electrophile, right? In theory, it could also take this proton. But when that happens, I can always just take that proton back off, right? This is reversible. So that certainly happens. It's just not a productive thing, and it just goes back until it finally adds in, right? So that's a good question. It can always do this with the carboxylic acid, but it's different. It's different down here because when this carbon picks up a hydrogen, you're never going to take that hydrogen back off. That's not acidic at all. So now this carbon has no electrons, has no lone pairs. There's nothing you're going to do um, to be able to regenerate that nucleophile once it's gone. That's a good question.
I have a question going off of that too.
Yeah.
So if it was a lithium, like just lithium instead of MgBr, would that do the same thing too? So if it has like a metal, would
Mhm.
it still? Okay.
Yeah, you do not want an OH around when you have any sort of carbon nucleophile because it will pick up that proton and be done.
I have another question on that one.
Yeah.
So for that, do you just end on the oxygen with a negative charge?
Yeah, but the more important thing is that this Grignard got quenched, right? The more important thing is that you had a negatively charged carbon with electrons, and now you don't. And now there's no way there's no free electrons to attack into.
Okay. Okay, thank you.
Right? There's no way to go back. All right. So hard and soft nucleophile, that just refers to okay. There's a couple of concepts kind of tied together here. A harder nucleophile, this is more basic, so it's more likely to take a proton. These are usually these are usually smaller charges. So like NaH is a hard nucleophile, right? It's just like this really hard like it's this kind of idea that this charge is concentrated. Whereas soft nucleophile, these are more nucleophilic. They're more likely to attack a carbon and less likely to attack, uh, hydrogen. So sodium hydride is hard. It's only going to really ever act as a base, where like these are spread out charges. So you see things like S minus and this. These are considered soft nucleophiles. If you think back to Orgo 1, these are things where the charge is spread out either over a large atom or over like resonance, right? Another one is copper lithiates. Because copper is such a big metal, it kind of helps spread out that charge. LAH, LAH. Again, aluminum is a big spread out charge, so it's going to be more nucleophilic. Where harder nucleophiles, these things tend to be, like N minus tends to be really hard nucleophile. H minus, NaH, um, R lithium, right? Because lithium is much smaller than copper, it tends to be a harder nucleophile. So there's just this relationship between how spread out a charge is on a nucleophile and how it acts more nucleophilic rather than basic. So some fair game questions would have to do with, um, giving you sodium hydride and giving you LAH and asking you which one reacts in which way, right? NaH is more likely to take a proton, where LAH is supposed to act like another one, or doing a similar question comparing like a lithiate versus a copper lithiate, right? Um, so I want you guys to be able to kind of make the relationship between a soft, more spread charge of a soft nucleophile being nucleophilic versus a harder, more basic nucleophile.
Oh, I have a quick question. This is like kind of a weird question, but like since like the softer like nucleophiles, they're able to like add in, but they're also like significantly bigger in size with like the atoms. So like copper, for example. Like how exactly does that work? Because that just seems like kind of weird to me, the fact that it's like so big, yet it's able to add in, while the thing that's so small is only able to take a proton.
Yeah, so I think you're getting the idea of sterics kind of mixed up with bulkiness. Um, yes, like an S minus is bigger than an O minus, but it's not exactly bulky. Um, so like you're saying, like a big bulky base like this, like why does this big S not act like that? Or this bigger thing?
Yeah, I guess. I mean, just because like with sulfur, you'd figure it's just like a bigger atom, even though it's like, it's only one thing.
Yeah, the explanation is really that the size of the atom is pretty inconsequential when you compare it like to something like tert-butyl, which has all of these branches. So it's really all these hydrogens that add the bulk, not the carbons themselves. So like it's really like this is significantly bigger than this, even though this atom is bigger than this one. Does that make sense?
Yeah, it makes sense.
So like the bulkiness of the size of the individual atoms isn't really consequential enough to play into that. But that's a good question. All right. Yeah, so here I see a Grignard, I see a metal. I'm going to go ahead and just rewrite it with a negative charge. I've got a nucleophile, I've got an electrophile. Adds in, kick up the electrophile. I broke a carbonyl. it wants to reform, but I don't have a leaving group, so it has no chance to reform. Can't go down. So I'm going to protonate it and we'll be done. So Grignards are easy. They're nice. We're good to go. All right. I've got a nucleophile, I've got electrophile, I've got no acid or base. So nucleophile attack electrophile. Takes up. Then I'm not in acidic conditions, so I don't need to do a proton transfer. So there's no acid here. This is actually net neutral. Even though you see a positive charge, it's net neutral, so I don't need to do anything. I can just collapse and kick off my best leaving group. And I form this. Then I'm going to neutralize my product. So this is a pretty simple one. Only a few steps.
Quick question. So since it's not in acidic conditions, you would use the chlorine that you kicked off instead of like a water since it's not in acidic conditions.
To be honest, I don't really care what you use here. You'd
Okay.
probably neutralize it with water anyways.
Okay.
Yeah, so if you use water, I don't care. You can, heck, you can write base for right here for all I care. Um, so sodium hydride, we know that is a non-nucleophilic base. It will never add into a carbon. So that's off the table. Um, so I see something that potentially looks like three electrophiles. Uh, but I do see a carboxylic acid that which in basic conditions can be deprotonated. And once it's deprotonated, I see pretty clearly that there's an electrophile right next to it that it can attack. So this is really just mainly getting you to see, hey, this carboxylic acid can be nucleophilic in basic conditions.
Like, the reason why you're attacking the carboxylic acid too would another reason just be is like the resonance because it's like more stable because as the negative oxygen can like kind of like it can collapse and form a bond and then like kick up into the other oxygen.
Are you asking why I took this hydrogen?
Yeah, is that like the another like good reason?
Let me see. Yeah, this is an acidic hydrogen, right? The carboxylic acid. Like this is not an acidic hydrogen at all. So this is the only, like I've got a base and this is really the only proton I can take.
How did you decide to um, attack the electrophile next to the carbon and not the um, the one on the carbonyl?
Yes, sorry. What is it? Okay, someone just knocked on the door and then I guess walked away. So it has to do with ring size. So if this were to attack all the way down there, it wouldn't be a reasonable ring. Does that make sense? Like if I were to come all the way down here to attack, that would create some monster ring. So it's going to form this little 5-membered ring first.
Okay, got it. Thank you.
I have a question about the previous question. No, when are we gonna kick off the chlorine instead of the oxygen? Or like, when are you gonna kick off the chlorine instead of using the oxygen's electrons?
You do kick off the chlorine.
Oh, wait. Okay, I just did not see that.
Yeah, you
Sorry.
kick it up right here. Yep. LAH. So I see. Sorry.
Why do we kick the chlorine in the last problem? Yeah, that one with the non-nucleophilic base. I mean with the NaH.
Because this is the electrophile right next to your nucleophile.
All right, got it.
All right. I've turned carboxylic acid into a nucleophile. There's an electrophile right next to it. H minus. LAH is, you can think of as a hydride source. This is a nucleophilic hydride, unlike NaH. It can add into that carbonyl. Pick up. I form a tetrahedral intermediate. When I break that carbonyl, it wants to reform. I have my best leaving group, which is that oxygen. So that opens up that ring. Then I've got all the equivalents of LAH in the world that I could want. So I see that there's another carbonyl that I've reformed. Whenever there's a carbonyl nearby, I can always add more LAH into it. I broke that carbonyl, it wants to reform, but there's no leaving group, so it can't. And the thing is, I've got 4 equivalents of LAH. When I look at this, is there anywhere else I can attack with H with the nucleophile? I mean, not
No.
really, right? There's no other electrophile, so it doesn't matter that I have excess. This is all I can do. There's nowhere else I can put an H minus. So at this point, I'm done using LAH, and so I'll just go and you can show both getting protonated at once. A couple common mistakes here is people protonating this negative oxygen at this step. But the thing is, water doesn't show up until after all the LAH has reacted, right? Quench with H2O means that at the very end is when the H2O comes up. So that gives me this. Gives me these 2 alcohols.
So whenever we are using LiALH, are we just automatically assuming that we're going to add into the carbonyl twice, or could we use the second hydride to like neutralize a negative oxygen after instead?
Hydrides can't neutralize a negative oxygen. They're both negative.
No, I mean like after the first add-in, instead of putting the hydride into the electrophile again, could we not just allow that negative oxygen to take that hydrogen?
What hydrogen? Which hydrogen? This?
Yeah.
No, because this has a negative charge. It's a negatively charged hydride. So those 2 negatives aren't going to come together.
You're right. Okay.
Yeah, this isn't an acid. It's a hydride. It's not a proton. It's fundamentally different because it's got a negative charge. So yes, it will keep adding into electrophiles because that's the things that want the negative charge. Yeah, good questions. All right, these next 2 questions were put together on purpose, right? Sodium hydride. That's a base. base deprotonate nucleophile. And now I have to decide whether I attack this or this part of the epoxide. Since this is a negatively charged nucleophile, it's going to attack the most convenient, the most accessible side of the epoxide. That gives me this. And then on a test, I would tell you that we can quench with water. But the key idea here is understanding which side in which conditions we attack an epoxide. Likewise here, I have an acid. So step one, I protonate my electrophile with my acid. And since I have a neutral nucleophile, this positively charged electrophile is going to kind of form the most stable positive charge. So that puts a positive charge over here. So when this nucleophile attacks, it's going to attack the more substituted side. So in acidic conditions, we're always going to attack the more substituted side of an epoxide. And likewise, I get here, and I need to neutralize it to create the final product.
Question on the previous one with the NaH. I thought you said that if there's an O negative, it can't take a hydrogen from a hydride because it's also negative. Or did I mishear? Like, did I understand you wrong?
Wait, what? Say that again?
Like, in the previous, like this on the NaH, when you took, a hydrogen in order to make it an OH, I thought that in the LH question you said that you couldn't. Oh wait, no, I'm sorry. I think I misheard you. I think I just wrote it down wrong. Thank you. Sorry.
Okay. All right, here, sodium hydride. This is the only even relatively acidic hydrogen. This is my nucleophile. This will likely be my electrophile. So base deprotonates nucleophile as well. So nucleophile attack electrophile. Kick up into the carbonyl. I broke a carbonyl. It wants to reform. I've got a leaving group, so I can kick that off. And then I form this. It's the same thing as earlier, except I just kind of switched the nucleophile and the electrophile, right? I get the same product, but I switched for the OH and the Cl word. So that's kind of showing you how.
Question, real quick.
What's up?
Sorry. So I know last class we talked about like the protecting groups. I included that in this. Is that like wrong? We should only be doing that in synthesis.
Yeah,
Because
yeah.
like
So
technically
here
there's
I'm
another
just
carbonyl.
here I'm giving you everything you need. here. You don't need to do anything like that. It's just one reaction.
Okay.
Yeah.
Okay. Thank you.
Yeah, that's only synthesis.
I have a question too.
What's up?
So is there a reason, or not is there a reason, but could you, instead of doing it in two steps, when you have the nucleophile attack the carbonyl, could you not just have the chlorine leave in the same step, or do you have to do that in two separate steps?
It always pushes up the carbonyl. So if there's a carbonyl part of your electrophile, it will always push up the carbonyl every time.
Oh, first. Okay, sorry. I thought I was doing it at the same time.
I have a question.
Yes.
Oh, wait, never mind. I just figured it out.
Um, I'm in acidic conditions, so this carboxylic acid is most likely nuclear or electrophilic. So protonate my electrophile. Nucleophile attack electrophile. Doot doot. OH. OH. NHH. Positive. Doot doot doot. All right. I broke a carbonyl. It wants to reform. My best leaving group is one of these OHs, so I'm going to take it. Take a proton from the nitrogen. I'm going to give it to one of these oxygens. They're the same, so it doesn't really matter which one. Then this is my best kicking group. I collapse and I kick. And from this, which needs to be deprotonated to form the neutral product. All right, so several steps, but it's the same steps we've been seeing over and over. I will say if you are struggling with the synthesis stuff, I would go back to that tetrahedral intermediate worksheet and make sure that you're following those rules, you know those rules, because that will kind of set everything up to be a little bit easier. All right, I've got a nucleophile, I've got an electrophile, I've got an acid. Step one, electrophile gets protonated by the acid. The trickiest part about this one is recognizing that this is going to be intermolecular. Nucleophile attacks electrophile, always push up to that carbonyl. It's going to be a 1, 2, 3, 4, 5 membered ring. Since this has a carbon on it, it'll be the better leaving group. So I'm going to take, we're in acidic conditions, so I'll take the proton from the nucleophile. I'll give it to the better of the two leaving groups. And then I have reformed my carbonyl. Yes? Is it locked?
Hey, Dr. Little, do you have the makeups?
Hold on.
There you
Uh, yeah, and then we just deprotonate to get the final product. Cool.
Dr. Little,
What's up?
is that a mistake when you got rid of the methyl attached? You wrote like OH2, right? Okay.
There you go. This probably isn't the best written question. You have two competing electrophiles here. Um, I would say, like in this case, I added this for a reason. This is the only nucleophile here. So I was just trying to keep you guys on your toes, throwing a random SN2 at you. So it just does that substitution. Okay. Here's another pretty simple question. So these copper lithiates have two equivalents, an equivalent on either side, but they act very similarly to just a Grignard. So thinking about this carbon being attached to a metal, having a negative charge, I've got one electrophile here, nucleophile attack electrophile, push up. We'll just use an R group here, save a little time. I've got no leaving group, so I can't reform my carbonyl. So I'm gonna just quench it with something, usually water. This is what we get. If you do use R groups in your thing, at least draw the final product completely correct.
And you would call that a hard nucleophile, right?
In this case, it's a softer nucleophile, but it doesn't really matter because I don't only have one thing to attack.
Okay.
Soft and hard only really talks about like relative nucleophilicity and basicity. Here it doesn't really matter. It's like it's not that helpful to talk about it unless I'm comparing two things. And here's another example of carboxylic acid in basic conditions. We deprotonate it and methyl bromide is my electrophile. So I posted this and then I kind of realized a couple of things. I didn't give you guys an imine and an enamine and an acetal formation in this practice. Those are still fair game. Like things that you did on the last couple of quizzes. If you're not sure what I'm talking about, go back and do the past two recitation worksheets. Those answers are up, by the way, so those would be good practice as well. Um, but it's really just following those tetrahedral intermediate worksheet rules, and you'll get an imine or an enamine. Like you guys have practiced for the past couple quizzes. So I didn't realize I hadn't put a question like that on here, but those are also fair game. Just because it's not on the practice test doesn't mean that it's not something that can be there if it's things that we've been practicing a lot on quizzes and tests and recitation worksheets and stuff. So yeah, just watch out for that. So I'll write that. I just thought I'd give you a little bit kind of more off the beat ones. I think you guys have shown to be pretty decent at these. All right.
On the test, are we gonna have to name the amine and amine and acetyls, like once we complete the reactions?
Um, I forgot to put it on the practice test, so I won't put that on the regular test. But I'll probably do that for test 3.
Okay.
Yeah. Okay, so someone asked for this the other day, and I thought it would be good to kind of summarize. So if I've got something that looks like that, my first thought is I've got a Grignard and a carbonyl, right? Because that OH is one away from the line. If I have this where the OH is 2 away from the line, I'm thinking epoxide. Right, that would be my first thought, a Grignard and an epoxide. You need both. If I see something like this, an ester, I'm thinking an acyl chloride and an alcohol. If I have a nitrogen carbon bond, probably fair to assume that I have a carbonyl with a nitrogen. What else? And these are kind of the main ideas, like the main major bond forming reactions that you guys will see. If there's more that we run into, then I'll backfill that in. All right. So I can already tell this is going to be a protecting group question because I have this amine that doesn't change. But my first thing is that's my major bond that I've got to explain. And I've got an OH that's 2 carbons away. So almost certainly I'm going to just kind of redraw my starting materials. And that was almost certainly an epoxide. And this was my Grignard. Now the thing is, I don't want any sort of NH2 or OH around a Grignard because it will wreck my Grignard. So I want to make sure that there's a protecting group on this nitrogen to help make that happen. And so I need to mention that I need to deprotect it. So I should talk about making 1 and making 2 in my mini synthesis. Because I've explained the major bond that I need to form. So 1 is made from this starting material. I'm going to add a protecting group. Then MCPBA creates my epoxide. And 2 is made. But again, I want to reiterate that this is the most important part of this picture. You can forget something here and we'll live to fight another day. But understanding the major bonds formations, that's the key. And to get more practice doing that, again, I would go back to those recitation worksheets. We did a lot of practice there. Okay.
For those types of problems, would you want us to include whether we need like an acid or base for the epoxide?
So this is by definition basic conditions because it's a Grignard.
Oh, okay, thank you.
Like a Grignard can't be in acidic conditions. No, that's a good question. If it was an alcohol, then yes. And there were some questions on some practice back at some point where that would be fair game.
For synthesis, is it okay if we end exactly where you ended, or do you want us to show like them relating after that too?
What do you mean?
Like we ended at like showing how we got to the two major products that we need, but we didn't show them like actually connecting to make the full product. Do you want us to still do that at the end, or just end where you ended?
I mean, if yeah, you can just like say, hey, this is gonna make this. That's fine. I don't think I fully understand what you're saying.
Like and like showing the Grignard actually attacking the epoxide
You don't have
in
to
the
show the
final step.
mechanism. No.
Okay.
I would see this. I would see that and think this. But the problem is that I have two carbonyls, and so I probably need to protect this one. So the product of this, so the acid and the reducing agent, the reductive amination, will get me that product, which then I can deprotect that acetal using H0 plus. So I need to explain getting this and this. So one I can make through just a protection, acetal protection. And then two I can make from an oxidation of that alcohol. All right. I see two major bonds I need to form, right? That one needs to be formed and this one needs to be formed. I'm not seeing an obvious reason to do one or the other. So I guess I'll work on the Grignard first. So these two things should make that. This isn't really a big problem. It's not an NH2. Don't I could protect it. Yeah, let's just go ahead and protect it. Let's be safe. So whenever I see an NH or OH, it's always kind of safe to protect it. So then I need to do another major disconnection here, which would be the carbonyl here and my nitrogen here. But you can see another problem here that I would have two carbonyls, which is less than ideal. So I need to protect one of them. So again, I'm going to show this. And then I need to deprotect to get to that product. And I think that's it. I think those are my two major bond forming reactions. So outside of that, I need to explain how I got to 1, 2, and 3. So 1 was, I can substitute that Br out with sodium hydroxide since it's primary. Then PCC gets me to 1. 2, I've got this starting material, which I can protect. Which that gets me to 2. And then 3 is just making my Grignard. So taking a really methodical approach and always protecting is safe. I realize I didn't explain the protecting group, so I'll just add that in. You can just protect.
Do you mind really quickly explaining like how like the amine adds into like the aldehyde with like the H2SO4 and the NABH4?
Why don't you get some practice and tell me what happens?
So the oxygen's gonna like take the hydrogen, it's gonna pronate it.
Mm-hmm.
And then the amine is gonna add into the carbon and it's gonna push up.
Mm-hmm. We'll shorthand this. Then what?
Um
Do you have a good leaving group?
the problem with like the amine now is like that it was just added in, so I don't think that can be the leaving group.
Nope. Do you have something else that could be the leaving group?
Um, I mean the OH, but I just don't know what you'd like push it with. Oh,
The nitrogen.
yeah.
And then you deprotonate it and form this, right? So that's the first step. That's 1. So this plus this and H2SO4, I mean, you can walk through the mechanism. It forms the imine. Then what is NABH4?
That's just like a base.
No. Close.
Reducing agent.
Reducing agent. It's like LAH, H minus. Since that imine is similar to a um, it's similar to a carbonyl, it acts as an electrophile, and you get this. So these are all reactions we've done before. We're just doing them all in one thing. Right? You form the imine, then you reduce using sodium borohydride.
So for the protonation of the alcohol into water, does it take the hydrogen off of the nitrogen, or does it need water to protonate it?
Yeah, so I mean, I shorthanded it here, which I wouldn't want you to do on a mechanism if I asked you the mechanism. But yes, a water will come and take this hydrogen from the nitrogen and give it to this oxygen over 2 steps. I just wrote proton transfer to just imply that that's happening.
Okay, cool. Thanks.
But yes. No, reaction like this is fair game for the test. But yeah, that's a good question. All right. Last one. I see this. It's a pretty easy disconnect for me. I find too many people getting so worked up about like I don't know how to make this that they don't put it here. But like this is more important. If you forget how to make this, you forget how to make this. But like this is worth half the points all by itself. Now, what's the problem with this? I have 2 alcohols. Which one's going to add into this carbonyl? I don't know. So I want to make sure I protect this one. So I want this alcohol to add specifically into this. You can, again, I would encourage you anytime you do a major bond formation, if you don't understand why you did that major bond formation, try the mechanism. You should be able to do the mechanism. All right, this adds in here, goes up here, it comes back, kicks off this chlorine, and now you've replaced the OH with the CO. And that's how you get this product. Then I'm going to evaluate this on its own merits, and I notice that that was a major bond formation. So that means that that looks like some kind of Grignard to me, which if I draw it out would make this.
Wouldn't the Grignard attack the H on the alcohol?
Yeah, so this you can see that this would make all sorts of issues, right? This is like this, and there's all sorts of problems here. Because then I couldn't selectively protect this over this. So I'm going to look back, and I noticed that I had a carbonyl here to start with. So maybe instead of having an alcohol here, it would have been better to have a protected aldehyde, a protected carbonyl. That would get rid of a lot of problems. Because now what I can do is I can say, one, I'm going to protect my alcohol. Well, actually, there's actually going to be a fair amount of things. So I'm gonna kind of talk about making this here in a second. So turning this into this, it's going to be a couple steps, which we'll talk about in a second. So this question kind of gets a little, there's a lot of protecting and deprotecting that has to go on to make this question work.
I have a question.
Yes.
I guess I'm just confused on how you turn the alcohol into like an acetyl. Would it be wrong to just write OPG on the end instead?
Where? Over
So,
here?
right, yeah, so you turn that OH into an acetyl. Could I just do OPG since I'm kind of used to doing like alcohols and like just writing PG by the alcohols?
Okay, so the reason why that doesn't work super well.
Because of the mini synthesis?
Well, okay, we can talk about it. We can look at it here. We need to also protect this alcohol, which means how are you going to unprotect this and then protect only this?
Yeah, it's a lot.
Right? Like it would be hard. Like if you deprotected and then you reprotected, how do you specifically only protect one of the alcohols?
Yeah, I don't know. So on that double-headed arrow, do we need to write when we're going down to the next one, like, do we need to write like remove PG?
Okay, so the double-headed arrows is working backwards. This is just me envisioning a Grignard here, because this is the most important bit. This Grignard adding into here. If you mess up the protecting groups or things are something like that fails, that's not nearly as important as saying, all right, at the end of the day, this Grignard needs to attack this carbonyl.
Okay.
Um,
So it's not, so we can turn OHs, alcohols, into acetyls if we need to.
Yes, and I'll show you how to do that in a second.
Okay.
It actually starts as a carbonyl.
Okay.
This is the starting material. So
Okay.
you're kind
That
of
makes
thinking about
sense.
it backwards. I'm more turning a carbonyl into an alcohol than turning an alcohol into a carbonyl.
Okay.
Because you're working backwards, you're thinking about it backwards, but it's okay. These are the major bond forming, right? Those are the two major bond formations that I need to think about. So I need to talk about making one. I need to talk about making two. And I need to talk about I need to talk about making three and making four. Because I haven't described how I make any of those. So, oh, weird. I'll just one. Okay. So for one, I need to I'm going to go ahead and just protect this carbonyl. Then I can oxidize the alcohol to get this. So that explains how I got one. Two is a Grignard. Three is the acyl halide. So I need to turn it into an alcohol, which I then can oxidize to carboxylic acid, and SOCl3, or sorry, SOCl2 will get me that. And four, so four is saying, how did I get from here to here? Right, so again, this is a protection deprotection game. So this is what I had. I'm going to go ahead and protect this alcohol. and then deprotect this. And then I need to turn that into an alcohol on the end, which we can do using LAH. So this one's a tough one. This one's got a lot of protections, deprotections, trying to play the protection games. If you mess up a protection or deprotection, it's not the end of the world. It's going to be kind of a minor penalty. What I really care about is these major bond formations. If it just so happens like you can't get it to work out, then don't freak out. Just keep doing what you're doing. If you're at a position where like, oh no, I've got to protect one alcohol over the other, just keep pushing forward and put something reasonable down. And we'll give you as much credit as we can. All right.
I have a question on how do you determine like which cut to make first, or does it not matter?
Sometimes it matters, sometimes it doesn't. Um, like I did the S. I'd usually make the ester cut first. Um, there's a couple of reasons for that, but mostly it just works out the best that way. um, it's the easiest thing to add late. So to make that cut first is good. Because like if we made the Grignard cut first, then we'd have to worry about like the Grignard adding into the ester, which we don't want to do. So making the ester cut first, I think, is always a safe bet. And outside of that, it often doesn't matter.
Okay, thank you.
Or sometimes you'll start working on it and be like, man, the protection deprotection stuff going on this direction is weird. So, all right. All right. Does anybody have any other questions?
I got a question about the one that you just, or like the one right above this one. At the end, you're going through the NH2 thing on the side there. Why did you reduce it with NaBH4? Was that just to show like how to do that, or
Oh,
is it?
see?
Are you talking about here? Like in here?
Yeah.
Oh, someone just asked me what was happening here.
Oh, okay. So
And so
yeah,
I was saying you can do the mechanism, like if you want.
got you. Okay,
Right.
but why did like at the end, why did you reduce with NaBH4?
Because I mean that's what we've been showing with these synthesis problems. He was asking what this like why am I doing H2SO4 and NaBH4?
Okay.
The NaBH4 is to reduce the imine which you form from the initial reaction down into the amine.
Oh, okay. So
That's,
you're just showing the react. Okay, I got
I was just showing this reaction. Yes.
Yeah. Okay, I didn't see that.
So
I have a general question about carboxylic acids.
I have a general answer about carboxylic.
Okay, great. So whenever we're talking about them, would you genuinely say because when we're talking about how Grignards take the hydrogen instead of adding into the electrophile, would you generally say that they're not very stable electrophile or nucleophiles for that reason?
They're not very good electrophile or nucleophile. The word stable is a loaded word.
Okay.
Stable is actually stable actually usually means less reactive. So like a carboxylic acid is a poor nucleophile when deprotonated because that negative charge is stable, but it can still be a nucleophile.
Okay, so how does that change whenever a metal is added into the equation? Does that make it less likely
What do you mean?
to be a good electrophile?
Uh, I don't know what you mean.
I think it's your Grignards will take the hydrogen instead of adding in. You
Yeah.
were saying that you would want to convert it to make it a better electrophile, which is what like begs the question of, so is it not generally a good electrophile then
It's
whenever
not
it
a
is
great
metals?
electrophile, no. And it will never be
Okay.
electrophile in basic conditions.
Okay, so in basic conditions then is when it's not a very good electrophile. It's not all the time.
Mm-hmm.
Okay. Is that
Yeah,
the
I mean,
same for
in
being in
acidic conditions, it can be an electrophile. Yes.
okay. And that's only, is that like a general rule or is that only when metals are applied?
Metals essentially imply that this can be a basic condition. So in basic conditions, a carboxylic acid is never going to be nucleophile or electrophile.
Okay.
Someone asked me for all the mini synthesis questions or reactions. Um, I thought you were talking about all the major bond formation reactions. Gosh, to do all the mini synthesis would be probably take a minute. We've kind of showed the major ones. You want to be able to form epoxides. You want to be able to form Grignards. You want to be able to form acyl chlorides. You still probably need to know how to do eliminations and additions. I mean, that's a throwback. You want to be able to specifically just go to an aldehyde or ketone with PCC. Um, let's see, is there anything else? I mean, maybe you can consider protection and deprotection of acetals. I mean, this is most of the new stuff, right? That you're gonna run into. There's some old stuff, and if you're struggling with that, like if you're struggling with stuff that isn't, this is all the stuff that we've covered kind of since test one. Test one was all the organic one stuff with the elimination substitution. That would take a little bit too long for me to review. I would go back to that um, synthesis video that I did at the beginning of the semester if you're still having trouble with the mini synthesis stuff. Because if it's not this, then it's that stuff, which would take me a second to walk through. Okay, so someone specifically asked, these are convenient ways to make OHs, make alcohols from a double bond. The big difference between the two of them is where it puts that OH. So one puts it on, if I'm looking at the double bond, one puts it on the less substituted side, and one puts it on the more substituted side of a double bond. But it's in relation to that double bond. One common mistake I see people make sometimes is, like if I've got this BH3 and AOH H2O2 it doesn't put the OH at the end. It's not a magical reagent that puts things at the end. It adds it to the less substituted side of the double bond. It's always in relation to that double bond. So don't just like think it always adds to the end. All right, any other questions?
I have a quick question for the last one. You showed how you kind of unprotected, or you protected the carbonyl and undid the acetyl in the mini synthesis. Is it okay if I did that in the major bond formation? I just didn't
Yeah,
show the steps.
to be honest, as we get more complicated, this kind of distinction between major bond forming reactions and mini synthesis falls apart. And that's fine as long as we can tell the general flow of what you're doing. As long as I can follow what you're trying to communicate.
Okay, got it. Thanks.
Yeah, that's a good question. And honestly, at a certain point, people just write this all forward, you know? All right, if there are no more questions, then I'm gonna hop off and start printing the tests. So,
I have one more question, sorry.
what's up?
I just wanted to make sure for NABH4, that reduces only aldehydes, ketones, and amines, right?
Um, NABH4, yes, does not touch esters or it's only aldehydes and ketones.
Okay, but we've been using NABH4 to also reduce amines, so does that not go in the same category?
Yeah, it'll reduce imines. Yes.
Okay.
Yeah.
Okay, thank you.
Yeah, just not really esters and amides. It's the big thing. Yeah, good questions. Well, thank you guys for hopping on. I'll post the video in case you missed part of it. But yeah, good luck tomorrow.
Bye.